Let us solve a problem. Let us find the coefficient of volume expansion for an ideal gas at constant pressure. This is what we are supposed to find. If we say that we are talking about an ideal gas, the first thing that we recall is the equation of an ideal gas. This is also known as the equation of state. From this, we know that the pressure is constant. This is constant. What really is changing is this volume and the temperature. Let us differentiate both sides. If we differentiate both sides, P remaining constant remains as it is, V changes to dV, NR being constant remain as it is, and T changes to dt. If we are increasing the volume by dV, this dV scales with the initial volume and the change in temperature with the coefficient of volume expansion. So if we replace this expression back here, we get V into gamma into dt, which equals NR into dt. This cancels off from both sides. PV here can be replaced with nRT, T becoming the initial temperature. Therefore, nRT into gamma is equal to nR, which gives us gamma to be equal to 1 by T. Therefore, if we expand a gas at constant pressure, the coefficient of volume expansion will be nothing but the initial temperature inverted. Let us look at another problem. Say the time period of a simple pendulum is 2 seconds. This is when it is checked at 20 degrees Celsius. We are supposed to find out the time period if temperature of measurement or temperature say is increased to 30 degrees Celsius. To solve this problem, let us recall what the time period of a simple pendulum is. The time period of a simple pendulum T is nothing but 2 pi root over L by G. If we increase the temperature, out of all these quantities, only L is going to change, which is the length of that simple pendulum. The length of that simple pendulum is going to increase as a result of the temperature increase. So as we increase temperature, this length, say the time period now becomes T dash, this becomes equal to 2 pi root L plus L alpha delta T. Say the alpha here of the material of the pendulum is say 1.2 into 10 to the power minus 5 per degree Celsius. So now the new time period is this. The difference in these two time periods is thus going to be t dash minus t, which is going to be 2 pi into root L by g minus root L plus L alpha delta t by g. This L can be taken out common. This root g can be taken out common. So we have root L by g common from both terms. And inside we have 1 minus this quantity, 1 plus alpha delta t to the power half. As we assumed earlier, because this quantity is very small than 1, we can expand this binomially and we can write this as 1 plus alpha delta t by 2. This quantity here is nothing but the initial time period. So this becomes, let's say this quantity is delta t, this is what we are required to find out. This is equal to the initial t, 1 minus 1 minus the alpha delta t. So we have 1 minus the quantity here, which is going to be nothing but minus half. Sorry, this 1 is going to cancel off. What we are going to have is half alpha delta t with a minus sign. Okay, we made a mistake here. This t dash is going to be this. So this entire thing is going to be something like this. This is basically coming from t dash and this quantity is coming from t. Hence we won't have a minus sign. Which is also obvious. We can do these kind of checks when we are making mistakes in exams. Say we are subtracting these two quantities and by chance or by mistake we end up subtracting this and get a wrong result. But we know that if the length of the time of the pendulum is increasing, its final time period should increase. So this quantity should end up being positive, which is this. Now we can replace what values we have. The initial time period was 2 seconds. The alpha is 1.2 into 10 to the power minus 5. And the delta t is 30 minus 20, which is 10. This is going to give us 1.2 into 10 to the power minus 4 seconds. So this is the change in time period if the temperature of the setup is increased to 30 degrees Celsius.